Every year the Nobel Prize in Chemistry goes to a discovery that gives the greatest benefit to humankind. And if there was ever a material that fits that description, wow, it might just be this one. We're talking about molecular supersponges, and they have the potential to solve some of the biggest problems on our planet. So let's dive in and see what makes them so special.
But here's the thing. This isn't just a story about molecules and labs. It all starts with a childhood memory, one of scarcity, but also one of hope. This quote from Omar Yaghi, one of the pioneers in this field, it takes us right to the human heart of this invention and the problem it was created to solve. So where did an idea this big, this world-changing, actually come from? Well, our story doesn't start in some fancy high-tech lab. Nope, it starts in a place where the problem this material would one day solve was a constant, desperate, daily reality. As a kid, Omar Yaghi and his family lived in a single room, and the arrival of the government water truck, which only came once every week or two, well, that was a frantic life-or-death event. That experience, that deep, personal understanding of what it truly means to not have enough water, that became the engine driving his entire life's work. So when Yaghi came to the US, he got into chemistry, but he got really frustrated with the traditional way of doing things, what he called shaking and baking, just mixing chemicals together and heating them up. The results are often messy and totally unpredictable. He had this vision for a new way, what he called rational design, where you could actually connect molecular building blocks with the same precision as Lego bricks. You could build totally new materials from the ground up with a specific purpose in mind. Okay, so what did Yaghi and his fellow pioneers actually build with these molecular Legos? They created a whole new class of materials called metal organic frameworks, or MOFs for short. Let's get into the science, because this is where it gets really cool. Okay, think of it like a molecular construction set. It's actually pretty simple. You've got these metal ions that act like the joints, or the cornerstones. And then you have these carbon-based organic molecules that are like the long connectors, or the struts. That's it. That's the elegant, simple principle behind these amazing materials. And what happens when you mix these two things together is, well, it's kind of magical. You'd think you'd just get a random chemical mess, right? But no. Because of the way their chemical bonds are structured, they spontaneously, get this, self-assemble. They click together all on their own into this perfectly ordered, crystal-like 3D structure, just filled with these tiny, uniform holes, or pores. And this picture shows you exactly what that looks like. This is MOF5, one of Yaghi's most famous designs from back in 1999. You can clearly see the metal cornerstones linked by those organic struts. And that giant yellow ball in the middle, that's not a thing. That represents the empty space, the huge open cavity that's built inside this tiny structure. Now, that internal space, it's not just a neat feature, it's a literal superpower. I mean, the sheer scale of the space inside these things it's almost impossible to wrap your head around. 7,000 square meters. Just take a second and try to picture that. What on earth could that number possibly have to do with something on a molecular scale? That is the internal surface area from a single gram of a MOF. 1 gram. If you could somehow take a pinch of this stuff, an amount that fits on your fingertip, and unfold all the surfaces inside it, it would cover an entire football field. I mean, that is just a mind-boggling amount of storage capacity. And when you look at the structure again, you start to see how that's even possible. Every single one of those little struts and joints creates a new surface on the inside. All those surfaces add up to create this unbelievable amount of room to trap and store other molecules. So you have the world's most powerful sponge. What can you do with it? Well, as it turns out, you can start going after some of the biggest, toughest problems we face, from water scarcity to clean energy to climate change. And this is where Omar Yaghi's story comes completely full circle. His team has developed devices using MOFs that can literally suck water vapor right out of the air, even in a super dry desert with less than 20% humidity. Then, when the sun shines on the material, it warms up and releases that captured moisture as pure, clean drinking water. That childhood whisper of the water is coming, he actually engineered it into reality. But the applications just keep going. You can apply this same idea to our atmosphere. By changing the size of the pores, you can design a MOF to selectively grab carbon dioxide molecules right out of a smokestack. And it's not just about trapping pollution. They're also a huge deal for clean energy. There are MOFs designed to store hydrogen fuel, which is notoriously hard to store, way more safely and densely than we can now. That's a huge step for making hydrogen-powered cars a reality.
And this right here shows why that's so critical for all of us. This graph lays out how vital technologies like carbon capture and storage, or CCS, are if we want to meet our climate goals. You can see from these different wedges, CCS is a major part of the solution, and MOFs could be a total game changer, making the whole process of capturing CO2 so much more efficient and cheaper than the methods we have today. So, this incredible journey, right, from personal struggle to a global solution, it all led to the absolute highest honor you can get in science. And so, in our hypothetical 2025, it happens. The Royal Swedish Academy of Sciences officially recognizes this paradigm shift in how we design materials, awarding the Nobel Prize in Chemistry for the development of metal organic frameworks. Now, a breakthrough this huge is never the work of just one person. The prize was shared by three absolute pioneers: Richard Robson in Australia, who laid the very first groundwork back in 1989, Susumu Kitagawa in Japan, who is the first to show how these frameworks could be flexible and absorb gases, and, of course, Omar Yaghi at UC Berkeley, who designed those incredibly stable and super porous MOFs that really unlocked their full potential.
And this timeline just gives you a quick snapshot of that journey. It starts with an initial kind of wobbly structure back in '89, then comes the big breakthrough with MOF5 a decade later. And finally, the Nobel Prize recognizing a field that has now exploded to create tens of thousands of these unique materials. I mean, from storing clean fuel to filtering pollutants to even delivering life-saving drugs right where they need to go in the body, the potential just seems endless. Which really leaves us with one heck of a question. With their power to solve so many of our most fundamental problems, could MOFs actually be the most important, the defining material of our time?